So the next talk is partial identification of those responses with hidden confounders. And the speaker is Myrl Marmarelis.
Marmarelis, yeah.
Thank you.
Hi, everyone. I'm Myrl. I'm from the University of Southern California. And I'd like to talk about a new way to do partial identification of those responses with hidden confounders. I'll start with the motivating example of why it's important to deal with hidden confounders. Here is a listing of New York Times headlines from over the years of the benefits of or possible non-benefits of drinking red wine. And I want to ask, why has it been so difficult to determine if red wine is good for us or not over the years? There's a variety of conclusions that have been drawn in the news, starting with thinking that even a little bit of alcohol is not good for you, and ranging to maybe actually a bit of red wine slows aging, or it keeps your liver healthy, ironically, or it helps with diabetes. So one of the reasons why it's been such a roundabout journey in our conclusions for how red wine affects health is that there are a lot of variables that mess with these conclusions. So for instance, the consumption of red wine tends to correlate with socialization, wealth, and the lack of certain diseases. And these introduce such strong associations that any observational study would be difficult to fully correct for, let's say. So this highlights an issue with causal inference that typical predictive tasks do not deal with. When in typical predictions, we try to describe things like, does this image contain birds? Does this text have positive sentiment? In causal inference, we want to predict what the outcome of an intervention on the world will be. So we have to care about variables that might get in the way of the intervention and the outcome. And these are known as confounders, or in some fields, we call it endogeneity. And usually we try to observe these confounders and then correct for them, and there are very many methods for that, but sometimes we can't observe all of them. And in that case, the next best thing is to make a reasonable structural assumption about the nature of these hidden confounders, and then produce a set of possible outcomes that are admissible under this constraint of a problem, and also that agree with the data. So the other part of the title is dose responses. These are simply causal outcomes when the treatment variable is a continuous real variable. And I think it's pretty clear that a lot of times when we perform observational studies, it's important to look at the amount of a treatment. For instance, when we're talking about prescribing dosages of some medicine, we look for the dose response curve, and we want to see which dosages are beneficial. So sometimes when we increase the dosage, it gets more and more helpful. And then at some point it becomes toxic if you have too much of it. And hidden confounders, some very simple and realistic situations in the real world might lead us to vastly overestimate the dosage that is helpful for certain drugs. Also, when we perform policy optimization and we want to perform, let's say, nudges and nudge one person to exercise a little more, maybe some people to drink less, the binary case of looking at no treatment or yes treatment is a little too coarse for dealing with these nudges. And instead, it's important to look at the causal derivative, the effect of incremental changes for individual people. Here, that is the derivative of the dose response at the treatment that we observe the current person. So it's helpful to look at dose responses for that reason. Now, here's a related phenomenon, the Simpsons paradox that a lot of us have probably seen. Sometimes it's helpful for just gaining intuition on what hidden confounders do. In many data sets, you might have subpopulations and they each exhibit certain trends as a response to some variable. And let's say the populations individually tend to have an upward trend, but when you average over the whole data set, you get a negative trend. And this could happen depending on biases and which parts of each of the subpopulation you observe. So this is pretty much exactly the problem of causal inference, just recast in different terms. So now I'm going to go into potential outcomes and then how we come up with our solution. We start with a predictive model. For our case, this is a conditional density function of the outcome y as a function of the treatment variable and also covariates. And the covariates hopefully contain as many confounders as we can observe. And we say that this predicts the potential outcome at t. So we use the notation yt to talk about potential outcomes. We say that because we also are concerned with, for each individual, what is their potential outcome at different t's? For someone who we've observed to smoke to some extent and also have different other variables in x, what would their health outcome have looked like if they had not smoked? So this is why we talk about potential outcomes. We want to be able to control for all the relevant variables in this individual and see what they would have looked like. And these are kind of like latent variables, we could say. So the target quantity that we want to estimate is the expectation of a potential outcome conditioned on the covariates. Now in potential outcome frameworks, one of the assumptions is the ignorability assumption, and this formalizes the need for no hidden confounders. It says that the set of potential outcomes should not have a statistical dependence with the treatment assignment once you condition on the covariates. This is very helpful because it simplifies how we could use the outcome model. If that's the case, that there's no dependence, we could simply condition on t, and then we could change t, and that gives us a prediction for the potential outcome, yt given x. However, if this is not the case, if the ignorability assumption does not hold, then we could have variables that influence both t and yt, the outcome, the potential outcome. And therefore, conditioning on t introduces more information about yt, and the outcome predictor could be arbitrarily biased. So in that case, we have to revisit the fundamentals. And we start with this equation that always holds, even if there are hidden confounders or not. We say that the potential outcome yt given x is an average over all these different treatment assignments that are possible that we've observed. And we average over this quantity that we cannot observe that is called the counterfactual. It is, what is this person's potential outcome at t given that they've been assigned tau and they have covariates x? We cannot observe this in the case of hidden confounding because this tau, we can only observe it when t is equal to tau. But when they're not, then these hidden confounders are biasing it. So there's no way to observe it. Another difficulty when we deal with continuous treatments is highlighted by briefly outlining how we do the partial identification for binary treatments first. So when we look at binary treatments, basically the integral is just a sum over two things. We have two possibilities, the factual and the counterfactual. So we could look at the potential outcome when the treatment assignment is t. And we also think about the counterfactual where the treatment assignment is the other t, not the one, it's 1 minus t. Because we have one known quantity and one unknown quantity, we could introduce some assumptions about the red part, and this lets us give bounds that are still informed about the potential outcome, yt. With continuous treatments, we've graduated to an integral. And the problem here is that the known part is infinitesimal, and we essentially cannot identify the integrand almost anywhere. So what we propose moving forward is to introduce an approximation and inflate the blue part into a somewhat knowable region in the integral. And with this, then once we do this inflation, we could cut up the integral into two pieces, the blue and yellow part as the known and the red as the unknown, and then follow a similar methodology as with binary treatments for partial identification and come up with somewhat informed bounds for the potential outcomes with continuous treatments. So this is how we do the approximation. We say that the counterfactual is roughly what we can predict, the factual, plus these two extrapolating terms by performing a Taylor expansion. This might seem helpful, but it's a little deceiving because we can't actually identify these derivatives. However, we are giving structure to the problem, so we're moving slowly in the right step. So here's the integral from before. We're integrating the counterfactuals, right? And we're also weighing, of course, by the propensity that we can observe. And this time, we split, as we said. So we introduce these functions called wt of tau, and they're equal to 1 when t is equal to tau, and they go to 0 as you move further away. So they give you this yellow region. And I'll discuss later how we come up with these, but let's just say that we have them. So it's also establishing a trust region for how much we trust the approximation. So we plug in the approximation, the red p tilde there, and the known part, and then in the other part, we keep it totally unknown. And we perform Bayes' rule, we rearrange things a little bit. And by rearranging things, we see that there's a potential outcome actually in the B part, right? Py of t given x. And that suggests that we could move it over to the other side. And we end up coming up with this representation of the potential outcome given x, where now we have a fraction of two integrals, both weighted by w, and the top has the approximation, the bottom has the totally unknown complete propensity, as we call it. And so I'll go later through, how to deal with the weights, but for now we have to deal with how do we bound the approximation and also how do we bound the denominator itself. So now I'm going to introduce the core contribution of our work, which is a new sensitivity model. We call it the infinitesimal sensitivity model, the infinitesimal marginal sensitivity model, delta MSM, as an homage to the marginal sensitivity model that people use for binary treatments. So with binary treatments, as we said, there are there's a factual and a counterfactual. And we tend to bound the radon-Nikodym derivative of those two to say that the ratio of their densities essentially is close to 1. And by saying that, we are constraining how much hidden confounders could affect our estimate, our causal estimate. With continuous treatments, of course, there's an infinite set of counterfactuals. So to draw a direct analogy, what we do instead is we bound the radon-Nikodym derivative of nearby counterfactuals, tau plus delta, tau plus delta versus tau. We bound the radon-Nikodym derivative of those two, and we introduce this omega quantity. And then by following Bayes' rule, it turns out that this is a ratio of two odds. The nominal propensities for tau plus delta versus tau, and this can be observed, of course, and what we call the complete propensities, which cannot be observed. And it's simply the propensities further conditioning on the potential outcomes themselves. You could think of it as the quantity you need to know in order to do exact point identification of the causal outcomes. And we're bounding this in terms of the nominal propensities odds. So once you take the limit of this delta towards 0, you rescale appropriately, you get this logarithmic derivative form where you have now the ratio of the complete propensity and the nominal propensity. And we introduce this one hyperparameter gamma that says how much hidden confounding there might be, how fuzzy our estimate is going to be. So you could also interpret this as saying, how much is the person's treatment assignment informed by a potential outcome? This could only be through a backdoor path, i.e. through a hidden confounder. So we almost have the necessary ingredients for completing the solution. We have first the delta MSM, and we say that it holds with some gamma. And the second assumption might be a little more dubious, but I'm going to motivate it, and I'm also going to relax it later. It's the anchor point assumption, where we say that the propensity densities are not informed by the potential outcome at some special value that we call tau equals 0. What we need to know for now is that this is necessary to solve the integrals. And informally, what it means is that hidden confounders matter less near this value. All right, so we're combining the ingredients slowly. We have the potential outcome defined in terms of this factor D times the outcome prediction itself. What's nice about D is that it has these following enjoyable properties. The bounds of D can be solved in closed form, and D also always includes 1. So the outcome prediction is always in the admissible set for the potential outcomes, which sounds like an obvious desire, but yeah, in a lot of attempts to do partial identification for continuous treatments, this has not always been the case. All right, so as promised, I'm going to now discuss what to do with these trust weights, WT. The argument we follow is that by the Taylor remainder theorem, the continuity of the counterfactuals with respect to the treatment assignment tau, the continuity of those densities, right, but with respect to the thing we're conditioning on, determines the error of this approximation. And if we follow through with Bayes' rule, these counterfactuals are related to the complete propensities. So therefore, the continuity of the complete propensities are suggestive of the continuity of the counterfactuals. And the Lipschitz constants are related. So we employ the heuristic now of looking at the nominal propensities and looking at how continuous they are as being informative of how much we could trust that approximation. So we go one step further and we say that these W's should have the same narrowness as the nominal propensities. And we say, in fact, that they should have the same form, the same parametric form. Like if the nominal propensities are beta densities, then so the W should look like betas, but of course they are recentered and rescaled because we want them to be centered at T and to take the value 1 at T and to go towards 0 as they move away from T. So given this, the bounds for the partial identification factor are given in terms of mostly integrals that involve the product of these weights and the nominal propensities. And we could solve these in closed form for various exponential families, beta, gamma, and Gaussian we have in the paper. And one last thing, just to tie up the loose end, is this anchor point assumption. So before, if you remember, we had the anchor point assumption at tau equals 0 always. Now we actually symmetrify it for the beta case where we have treatments within the unit interval from 0 to 1. So we say that for the most distant potential outcome, the anchor point assumption should hold more strongly. In other words, the anchor point assumption at tau equals 0 should hold when we're looking at potential outcomes for T far from 0, like T close to 1. And vice versa, when we're looking at potential outcomes close to 0, we have the anchor point assumption being imposed for tau equals 1. So this new interpretation says that the potential outcomes, their informativeness of the complete propensity depends on how close they are to the value of the treatment assignment. So going back to the wine example, just to give an illustration, if we're trying to answer the question of, are you the kind of person that, let's say, drinks a lot of wine, so tau equals 1, the piece of knowledge that would be most helpful in answering that question is the health outcome at T equals 1, so drinking a lot of wine, not the health outcome from drinking no wine. And vice versa, if we're trying to answer the question of someone is the kind of person that doesn't drink any wine, then Y0 is more informative than Y1. The health outcomes from drinking no wine versus from drinking a lot. We have to look at these in the nested fashion. Like once we ask the question, which is more helpful? You can't compare across. And putting together these heuristics and also the solutions given the new sensitivity model, we performed some extensive semi-synthetic benchmarks where we took these large data sets that are high dimensional. We projected them randomly into various confounding variables and treatment variable. And then we created a lot of fake outcome functions that are random quadratic forms of these variables, because you need to know the outcome in order to do benchmarks, right? And we sampled 500 realizations of all these different semi-synthetic cases. And the task that we proposed was seeking to cover 90% of the real dose response. So how much do you have to grow this gamma parameter until you reach 90% coverage? And then we measured the size of the intervals, and a method that is more informed by the data and uses it more efficiently should cover the dose responses more quickly without having to grow the bounds as much. So we found that our method tends to be more efficient in this sense, compared to the recently proposed CMSM and also some baselines. And we tend to beat them almost 80% of the time. So that's quite exciting. Just to emphasize the contribution of this work, we described the first sensitivity model for continuous treatments that changes with the propensity and in a sensical way. And it also always admits valid potential outcome densities. We empirically demonstrated through these semi-synthetic benchmarks that the performance that these assumptions and the heuristics we made make sense, and it is seen through the performance. And also, I'd like to emphasize that this is pretty easy to use in a lot of observational studies. You just need an outcome predictor and a nominal propensity density function. And for instance, in our paper, we have a case study on the effect of different diet scores on brain health. because we looked at some biobank data that we also show in this benchmark. So yeah, thank you very much. I'll receive questions now.
So the discussant is Xingyuan Zhao. I think he's in the room as well. Or, oh, pardon, he's virtual, my apologies. So I'll do the clicking for you.
Yeah, I've just one slide, so it's an easy job for you. Yeah, I'd like to thank the organizers for inviting me to discuss this very interesting work. So this work, the main contribution is to extend the existing marginal sensitivity models to the setting of continuous treatment. So there are two ways to think about marginal sensitivity model. The first way, which is how I normally think about it, is this bounds the odds ratio between the propensity score, the observed propensity score, which is the probability of the treatment given the covariates, with the kind of the full propensity scores, the probability of the treatment given the potential outcome and the covariate. So it bounds that odds ratio between 1 over gamma and gamma. So equivalently, this can be thought as bounding this density ratio between the counterfactual and factual potential outcome distributions. So this is very much related to Rosenbaum's sensitivity model, if you're familiar with that. But one nice thing that works quite nicely with this particular form is that when you consider inverse probability weighted kind of estimators, because this directly bounds the odds ratio between the observed propensity score with the full propensity score, this gives you simple bounds to your IPW-based estimators. So the main contribution of this work is a new infinitesimal marginal sensitivity model, which I'm repeating the equations here, slightly rephrased terms. So one thing I noticed when reading the paper was that I think the authors assumed the domain of the treatment is 0, as a unit interval from 0 to 1 in the supplement. At least this seems to be needs to be bounded because some Taylor approximation was used, and eventually some argument was needed to say that approximation is not too bad, even if the treatment is even if you're considering a different treatment. So as we have seen in the talk, the main method is based on the heuristic that you can write the distribution of the potential outcome given the covariates in this form. And there's a sort of this notion of trust region or trust weight W in this approximation. And here P tilde is a quadratic approximation to P found by doing a Taylor expansion. So I have 3 comments that were more like questions that I had while reading the paper. I have to admit that I don't entirely understand the paper, so these comments could be quite superficial. My first comment is that regarding this approximation, this approximation is exact if P tilde is an exact approximation of is exactly equal to P, and this is exact for any choice of the weight W. This can be proved by a simple application of the Bayes formula. So the paper has developed some choices of the weight WT. Some of them that were explored in the supplement involves a beta density-like function, and it's emphasized in the supplement that this precision parameter in the beta density needs to be very large for that approximation to be accurate. But this seems to basically amounts to take that WT to be very close to a Dirac delta function at T. So I'm a bit confused by the suggestion that this beta form of the weight needs to have matching precision parameters as the true treatment. So I didn't quite get that point. My second comment is that it's not very clear how good this approximation is if p tilde is just a quadratic function. The paper did not provide any guidance on tuning parameter selection, which is quite essential for these sensitivity models. So for me, sensitivity analysis is not about sort of performing better or making better estimation of the causal effect. It's about what kind of reasoning, what kind of argument you can give when no measured confounders is not exactly true. And there's not much guidance on how the tuning parameters can be chosen along the way. My third comment is just on this, what the authors call the anchor point assumption that seems to be quite strong. Although there's some relaxation in the paper, it's still not very clear whether this assumption is actually true in any practical example. Thank you very much.
Thank you for the summary and also for the good questions. I'd like to say that, first of all, the treatment domain, we don't assume it to be bounded. It could also be unbounded as long as the weights decay to 0. So that's one part. We mentioned the main paper. I think also, so comments 1 and 2 could probably be addressed together. We propose this heuristic where we set the weights to be exactly equal in width, let's say, to the nominal propensities. So it's adaptive and it depends on the person's treatment propensities. And it's not, they're not very narrow. So it's not close to the Dirac delta. And yeah, so we do discuss a bit, how to tune this. We found this very natural heuristic and we find that it works very well in our benchmarks. Of course, there are other ways to look at how to find these weighting functions. And for the third assumption, it's true that the anchor point is rather strong depending on how you look at it. I think it's not as strong for Gaussian treatments, let's say, where you're looking at the effect of disturbances on some outcome variable. In that case, 0 is a natural choice for an anchor point where you don't care as much about the effect of confounding. And then also I mentioned how with beta treatments, we look at the symmetric version of it. And yeah, I think the numbers speak for themselves in the benchmark, but it's true. It's something you need to consider. So yeah, thank you very much.
Thank you. Pardon, we have time for a very quick question if someone in the audience has a itching question. Yes.
So you just said that in the benchmark, your stuff works, but in the benchmark, you assume that P tilde is exactly P, right? Because you assume the second order Taylor expansion in the way that you generate the data. So of course it's going to work.
We don't formulate the complete propensity. The propensities are in terms of the statistical dependencies that exist in the real data, and we randomly project it, and then we use those projections which have the statistical dependencies that exist in the data. We construct a fake outcome that's true, which is a quadratic form, but that is not the same as the complete propensity, which we're doing as a counterfactual. So in terms of the treatment assignment, I don't believe it is an exact approximation because we don't observe the actual confounders, right? So in that case, we can't. Yeah, it's different. So it's the approximation does not hold in the semi-static benchmark. But I'm happy to take it offline too. That's a good point. Yeah, thank you.
Okay, thank you.
Thank you, everyone. This concludes our session. Thanks to all the speakers and discussants. Thank you.